Have you ever just stopped and really thought about the device you're watching this on right now? I mean, how do we go from these room-sized machines that could barely do basic arithmetic to literal supercomputers that we carry around in our pockets? It is, without a doubt, one of the greatest engineering stories of all time. So, let's dive into this incredible quest for speed.
And just to wrap your head around the sheer scale of this, let's look at the numbers. ENIAC, one of the very first electronic computers, was an absolute monster. We're talking 30 tons, taking up over 1,500 square feet, and it could perform about 5,000 additions per second. Now your phone? It breezes past tens of billions of operations every single second. That mind-boggling leap? Well, that's the mystery we are going to unravel today.
So how did this all even begin? Well, it all started with a single, brilliantly simple idea that became the blueprint for pretty much every computer ever made sense.
It's called the von Neumann architecture, and the concept itself is surprisingly easy to get your head around. Just imagine a chef. That's our CPU, the central processing unit. Now, this chef has only one pantry, and that's the computer's memory. So to do anything at all, the chef has to run to the pantry to grab a recipe, that's an instruction, and then run back to the pantry to get the ingredients, that's the data. Everything, and I mean everything, comes from that one single place.
And this setup leads to this fundamental three-step dance. Fetch, decode, execute. The CPU fetches an instruction, figures out what it's supposed to do, and then, does it. For decades, the main way to make computers faster was just to make this single loop run faster and faster and faster. But as you can probably guess, this created a huge, huge problem.
And that brings us to the first major villain in our story, the Great Memory Bottleneck. You see, the processor started getting way too fast for its own good. Our chef, the CPU, became lightning fast, just incredible. But the memory, our pantry, was still way, way down a long hallway. The CPU could perform an operation in a tiny fraction of a nanosecond, but fetching the next instruction or piece of data from memory took many, many times longer. So the CPU was spending most of its time just sitting there, waiting around. This is famously, or maybe infamously, known as the von Neumann bottleneck.
So, what do you do? I mean, seriously, if your super fast chef is always waiting on the pantry, your whole kitchen just grinds to a halt. This was the central challenge for early computer engineers. How do you solve the waiting game?
The solution they came up with was just ingenious. Don't have just one pantry, have a whole hierarchy of them. The absolute fastest, most immediate things the chef needs are kept in registers. Think of this as the chef's tool belt. The next most likely ingredients are on the countertop, in a small, super-fast memory called the cache. And only when something is in either of those places does the chef have to make that long trip to the main pantry. This all worked because of a principle called locality of reference, which is just a fancy way of saying that programs tend to use the same data over and over. So by keeping it close, you slash that waiting time.
Okay, so we've made getting things from memory way faster, but the CPU itself is still doing just one thing at a time. Fetch, decode, execute. What if we could do more?
Well, the solution is called pipelining. The best way to think about it is like a car factory. Instead of one person building an entire car from scratch, you've got an assembly line. While one station is putting on the wheels, the station right before it is installing the engine on a different car. Pipelining does the exact same thing for computer instructions. While one instruction is executing, the next one in line is being decoded, and the one after that is being fetched. The goal? To have a completed instruction pop off the end of the line every single cycle.
But assembly lines, they hate surprises. They need a predictable flow. So what happens when the program hits a fork in the road, like an if statement? We don't know which instructions to load into the pipeline next until that if is finished. So does the whole assembly line have to stop and wait? Because if it does, you just threw away all of your performance gains.
And here's where it gets really, really clever. Engineers developed something called branch prediction. The CPU basically becomes a fortune teller. It looks at that if statement and, based on what happened in the past, it makes an educated guess about which path the program is going to take. Then, it just starts pulling in instructions from that predicted path to keep the assembly line full. And the amazing thing is, it's right more than 90% of the time. It's like having a little crystal ball inside your processor.
All right, so now we have a fast memory system and we have this incredible instruction assembly line. For decades, we just kept cranking up the speed of that line. But then, around the mid-2000s, we slammed headfirst into a hard, physical limit.
For the longest time, all of this progress was driven by Moore's law, this famous observation that we could cram more and more transistors onto a chip.
And you can see that exponential growth right here. We went from a few thousand transistors in 1971 to nearly a billion by 2008. More transistors meant more features, bigger caches, and faster speeds. But it came at a cost.
And this chart right here, this is the climax of our story. This is the power wall. Around 2005, you can see that the growth in clock speeds just stops. It flatlines. But at the same time, look at power consumption. It's skyrocketing. Why? Because making those billions of tiny transistors switch faster and faster was generating an absolutely insane amount of heat and using way too much power. We just couldn't cool the chips down anymore. The old way of getting more speed, it was officially over.
So if you can't make one engine go any faster without it melting, what do? Well, you add more engines. And this is the era of computing that we live in right now.
The entire industry pivoted. They moved from trying to make one single, incredibly fast master chef to putting multiple, simpler, and more power-efficient chefs on the same chip. This is exactly what a dual-core or a quad-core processor is. Instead of one core trying to do everything at 5 GHz, you have 4 cores working together at a more manageable 3 GHz. It was a fundamental shift from raw speed to parallel processing.
But of course, there's a catch. It's summed up by what's known as Amdahl's law. It basically says that adding more chefs only helps if the recipe can actually be split into parallel tasks. If you have to bake the cake before anyone can frost it, all the extra chefs just have to stand around and wait for that one single threaded step to finish. And this is the new bottleneck that software developers are constantly fighting against.
So when you look back, the whole history of computing speed is really a story of identifying and solving one bottleneck after another. The slow memory bottleneck, that gave us caches. The one instruction at a time bottleneck, that gave us pipelining. And the heat and power bottleneck, well, that gave us the multi-core processors that are in every single device you own today.
And all of this leaves us with a final, really exciting question. We overcame the power wall by building more cores, but that just created a new software challenge. So what's the next great wall in computing? Is the solution going to be even more specialized chips, a revolution in software, or something totally different, like quantum computing? The quest for speed, it never ends.